Namaste and welcome, folks, to another deep dive. You know that feeling when you really want to get your head around something, not just skim the surface, but understand the proper inside story?
Yeah, really understand it properly.
Exactly. That's what we're aiming for today, with something truly at the heart of our Earth. Magma. Think of it like the planet's own, well, internal hot sauce, maybe. The molten rock behind so much of what we see. Volcanoes, mountains.
Absolutely. We're going to look closely at this magma, what it actually is, where it comes from, deep inside, and why it behaves in such, well, dramatic ways sometimes.
Right.
We've gathered some really great information here, starting from the basics, but also getting into some the pretty fascinating details.
Yeah.
Our goal today is simple. Make this fiery mystery clear and interesting for everyone, whether you're just starting out, curious, or you already know a fair bit about geology.
Okay, let's try to understand this properly then. What exactly is this magma thing?
Well, in simple terms, it's rock. Rock that has melted and is sitting underneath the Earth's surface.
So underground liquid rock.
Basically, yes. But it's not always just plain liquid, you see. It can also have solid bits floating in it, like crystals that have already formed, and even little bubbles of gas trapped inside.
Okay. So it's a mixture.
It often is, yeah. And here's a really important point to start with. Every single igneous rock you've ever seen, your granites, your basalts, all of them, they all started their life as this magma.
Every single one. Wow.
Everyone. So if you want to understand a huge chunk of our planet's geology, you really have to understand magma. And it's not just Earth either, is it? Other rocky planets, they have magma too, or did.
Right. Mars, the moon, places like that.
Yeah.
Okay, so it's fundamental. You said it's hot. How hot are we talking?
Very hot. Magma is a complex fluid, usually at extremely high temperatures. Generally, most magmas are somewhere between, say, 700 and 1300 degrees Celsius.
700 to 1300 C. That's incredibly hot.
It is. But listen to, there's some, let's see, unusual cases. Carbonatite melts, which are quite rare. They can actually be as cool as about 600 degrees Celsius.
Only 600. Still hot, but much less than 1300.
Relatively speaking, yes. And on the other extreme, you have things like carbonatite melts. These were much more common way back in the early days of Earth. And they could have been as hot as maybe even 1600 degrees Celsius.
1600. Unbelievable. But mostly you said they are silicate solutions. What does that mean?
Right. Most magmas are primarily composed of silicon and oxygen bonded together, much like silicate minerals, which make up most of the Earth's crust and mantle. So a silicate solution is basically molten rock rich in silica.
Okay, and this hot, sticky silicate stuff, it doesn't just sit quietly down there, does it? It's active.
Exactly. It's dynamic. Magma has the power to push its way into the surrounding rocks. They call that an intrusion. It forces itself into cracks or weaknesses.
Intruding into existing rock. Okay.
Or it can find a path all the way to the surface and come bursting out as lava. That's what you see in a volcanic eruption, the flowing rivers of molten rock.
Right. Lava is magma once it reaches the surface.
Precisely. And sometimes the eruption is much more violent. It can be ejected explosively as tephra.
Tephra? What's that?
Tephra is basically all the fragmented stuff thrown out during an explosive eruption. So ash, pumice, bits of broken rock, even larger volcanic bombs. And when all that material settles down and solidifies, it can form a type of rock we call pyroclastic rock.
Pyroclastic. Pyro for fire, clastic for broken bits.
You got it. Imagine a massive fiery explosion throwing out hot rock and ash.
Okay. Now, where does this magma actually form? It's not just everywhere underground, is it? There must be specific places.
That's right. The location where magma forms is strongly linked to what it's made of, its composition. We see magma being generated primarily in a few key geological settings.
Such as?
Well, subduction zones are a big one. That's where one tectonic plate slides beneath another. The process releases water, which lowers the melting point of the mantle above it.
Okay, subduction zones. Where else?
Also in continental rift zones, where the Earth's crust is being stretched and pulled apart. This thinning allows hotter mantle material to rise closer to the surface.
Like the East African Rift.
Exactly like that. Then you have mid-oceanic ridges, those underwater mountain ranges where new ocean floor is constantly being created as plates pull apart. Lots of magma generation there.
Right, where the seafloor spreads.
And finally, you have hotspots, places like Hawaii or Yellowstone. The thinking here is that these might be caused by mantle plumes, basically columns of exceptionally hot rock rising from deep within the Earth, maybe even from the core mantle boundary.
Mantle plumes, okay. So these specific environments control where magma forms and often what type?
Precisely. We won't dive too deep into the specifics of each environment today. That's maybe for another time, but it's crucial to know these are the main magma kitchens, so to speak.
Magma kitchens, I like that. And once this magma is cooked up, is its recipe fixed? Or can it change?
That is a very important point. The composition of magma is definitely not fixed. It can change. It evolves.
How does it evolve?
There are several ways. One major one is fractional crystallization. As the magma cools, different minerals start to crystallize out at different temperatures.
Like we talked about with the soup analogy earlier, some ingredients solidifying first.
Exactly like that. So if those early formed crystals settle out or are separated from the remaining liquid, the liquid part, the remaining magma, will have a different composition than what it started with. It becomes, differentiated.
Okay, so it changes as it cools and solidifies partially. What else?
Magma can also get contaminated. As it moves through the crust, it can melt and assimilate some of the surrounding rock, the country rock. This changes its chemistry.
Like adding a different ingredient to the soup midway.
A good way to put it. And finally, different batches of magma can sometimes mix together underground. You might have two different magmas meeting and mingling, creating a hybrid composition.
Right, mixing different soups together. So fractional crystallization, contamination, magma mixing, lots of ways for it to change.
Definitely. Magma chambers are complex systems.
Okay, so we know what it is, roughly where it forms, and how it can change. But let's go back to the very beginning. What actually makes solid rock deep inside the earth melt in the first place? What are the key factors?
You can boil it down to three main physical parameters, three key factors that control the melting of solid rock into magma.
Three factors. Okay, what are they?
Temperature, pressure, and composition. Think of them as the three main dials you need to adjust to get melting.
Temperature, pressure, composition. Let's take temperature first. That seems obvious. Heat things up, they melt.
Generally, yes. For any given rock type, under a specific pressure, there's a temperature called the solidus. If the rock's temperature goes above its solidus, it will start to melt.
The solidus, the melting point under those conditions.
Pretty much, yeah. Now, inside the Earth, the temperature naturally increases as you go deeper. We call this the geothermal gradient.
Right. It gets hotter the deeper you go. How much hotter?
On average, it increases by about 30 degrees Celsius for every kilometer you descend. But, and this is important, this gradient isn't the same everywhere on Earth.
It varies.
Oh, yes, significantly. In some places, like deep oceanic trenches or subduction zones where cold plates are descending, the gradient might be much lower, maybe only 5 to 10 degrees per kilometer.
Okay, cooler regions deep down.
But in other areas, like under mid-ocean ridges where hot material is rising or in active volcanic regions, the gradient can be much, much higher, sometimes 30, 50, even up to 80 degrees Celsius per kilometer.
Wow, that's a huge difference. What causes the heat anyway? Is it just leftover heat from Earth's formation?
That's part of it, residual heat. But a significant amount of Earth's internal heat is also continuously generated by the decay of radioactive elements like uranium, thorium, and potassium distributed within the rocks.
Radioactive decay. So that's constantly adding heat. Okay, so high temperature is key. What about the second factor, pressure? How does that cause melting? I think pressure would keep things solid.
That's generally true. Higher pressure usually increases the melting point of rock. But there's a process called decompression melting.
Decompression. So reducing pressure.
Exactly. Imagine you have a parcel of hot rock deep within the mantle. It's hot, but the immense pressure is keeping it solid. Now, if that rock starts to rise upwards, perhaps due to mantle convection,
It moves towards the surface.
the pressure on it decreases because there's less overlying rock. Even if its temperature doesn't really change much, that drop-in pressure can lower its melting point below its actual temperature.
So the pressure drops, the melting point drops, and suddenly it's hot enough to melt.
Precisely. It crosses its solidus just because the pressure went down. This is a really important mechanism for generating magma, especially at mid-ocean ridges and hotspots. It's kind of like taking the lid off a pressure cooker allows things to change state.
That makes a lot of sense. Okay, temperature and pressure. The third factor was composition. How does what the rock is made of affect melting?
Composition is fundamental. The specific mix of minerals in a rock determines its overall melting behavior, its solidus temperature at any given pressure. Some rock types simply melt at lower temperatures than others.
So some rocks are just easier to melt.
In essence, yes.
Yeah.
The bulk chemical composition of the rock is the primary long-term control. But it's not just the main minerals. We also need to consider volatile components.
Volatiles? You mean like water?
Exactly. Water and carbon dioxide are the most important volatiles in this context. They can be trapped within the crystal structures of minerals or exist as fluids in the rock. And even small amounts can have a huge effect on the melting point.
How huge!
Well, for instance, adding just about 1% water by weight to a rock can lower its melting temperature by as much as 100 degrees Celsius.
100 degrees just from a tiny bit of water.
Yes. It works by disrupting the chemical bonds in the silicate structure, making it easier to break apart into a liquid. This is incredibly important in subduction zones, where water is carried down by the subducting plate and released into the overlying mantle wedge, triggering melting.
So water acts like a flux, making things melt easier, like adding salt to ice.
That's a perfect analogy. And conversely, if a magma loses its volatiles, perhaps as it rises towards the surface and the pressure drops, allowing gases to escape, its melting point can actually increase, potentially causing it to start solidifying again.
Okay, fascinating interplay. Temperature, pressure, and composition, especially volatiles. Now, you said melting starts when you cross the solidus. Is it like flicking a switch, the whole rock becomes liquid instantly?
No, not at all. It's usually a gradual process called partial melting.
Partial melting, because rocks are mixtures.
Exactly. Most rocks are made up of several different minerals, and each mineral has its own unique melting point and behavior under changing temperature and pressure. It gets quite complex, involving things called phase diagrams.
So as conditions change, some minerals start melting before others.
That's right. The minerals with the lowest melting points will liquefy first, forming small amounts of melt, usually along the boundaries between the mineral grains.
Tiny droplets of liquid between the solid crystals.
Yes. And as melting continues, these melt droplets grow and start to link up, forming interconnected networks. This also causes the rock's overall volume to increase slightly, and it starts to soften, losing its strength.
And does it take a lot of melting for the liquid to actually move?
Not necessarily. Under the immense pressures deep within the Earth, even a very small percentage of partial melt, sometimes just a fraction of a percent, maybe 1 or 2%, can be enough for the liquid to be squeezed out from the remaining solid crystals.
So even a little bit of sweat from the rock can escape.
A good way to think of it. This initial melt can then migrate upwards and accumulate. Typically, partial melting might proceed until you have maybe 20% or perhaps up to 35% liquid.
Why not more? Why doesn't the whole rock just melt?
Melting consumes a lot of heat, so it can be self-limiting unless you keep adding heat or reducing pressure. Also, once you get much beyond, say, 35–50% melt, the mixture stops behaving like a solid matrix with some liquid and starts behaving more like a liquid, containing suspended crystals or crystal mush.
Ah, so it becomes mobile as a whole unit.
Right. This crystal melt mush is less dense than the surrounding solid rock and can start to rise bodily as a large blob, which we call a diapir. And as this diapir rises, it experiences lower pressure, which can cause even more decompression melting.
The process feeds itself. Okay, partial melting is key. Now, scientists talk about different kinds of melts, primary melts and parental melts. What's the distinction there?
Good question. A primary melt is basically the definition of the very first liquid that forms when a rock begins to melt. It represents the initial composition produced directly from the source rock before any modification like fractional crystallization or contamination has occurred.
The pure initial juice squeezed from the rock.
Exactly. But finding true unmodified primary melts in nature is actually quite rare. Magma starts changing almost as soon as it forms and moves. One place we might see something close is in certain features within migmatites.
Migmatites, mixed rocks.
Yeah, rocks that have partially melted and then resolidified. They often have distinct light-colored layers called leucosomes, which are thought to represent the extracted melt fraction, potentially close to a primary melt composition from the crust.
Okay. And what about primitive melts? Is that the same thing?
Primitive melt is often used specifically for primary melts derived from the Earth's mantle. These are particularly important because studying their composition gives us clues about the composition of the mantle itself.
Ah, a direct sample from the deep Earth.
Exactly. By analyzing primitive magmas, scientists can model the chemistry of the mantle source region and understand how the mantle has evolved over geological time. It's a crucial window into the planet's interior.
So primitive melts are invaluable for understanding the mantle, but what if you can't find a primary or primitive melt? What's a parental melt?
We often use the concept of a parental melt when we're studying a suite of related volcanic rocks, say a series of lava flows from the same volcano. And we suspect they evolved from a common source magma, but we can't find the original unmodified one. A parental melt is defined as a magma composition, which might itself be somewhat evolved, not necessarily primary, from which all the observed variations in the rock suite could have been derived through processes like fractional crystallization.
So it's like a hypothetical starting point for a family of related magmas.
Precisely. Geologists will propose a potential parental magma composition, and they use computer models simulating fractional crystallization to see if they can reproduce the chemical trends seen in the actual rock samples. It's a way of testing hypotheses about magma evolution in a volcanic system.
Makes sense. Working backwards to find the common ancestor, so to speak. Now, you mentioned earlier that the degree of partial melting is important. How does the amount of melting affect the magma type?
It has a huge influence, yes. The degree of partial melting strongly controls the chemistry of the resulting magma, particularly the concentration of certain trace elements.
Trace elements?
Yeah, elements present in very small amounts. We often look at the ratio of incompatible elements to compatible elements.
Okay, explain those terms. Incompatible versus compatible.
Sure. Incompatible elements are those that don't fit comfortably into the crystal structures of the main minerals in the source rock, usually the mantle in this case. So when a small amount of melt forms, these elements preferentially leave the solid minerals and enter the liquid melt phase. They get concentrated in the first bit of melt.
They'd rather be in the liquid. Like what elements?
Things like potassium, rubidium, cesium, barium, uranium, thorium, the larger ions, often. Compatible elements, on the other hand, fit quite nicely into the mantle minerals, like olivine and pyroxene. Examples include nickel and chromium. They tend to stay behind in the solid residue unless melting is very extensive.
Okay, so by comparing the amounts of incompatible versus compatible elements in a magma,
We can estimate how much partial melting occurred. A small degree of melting will produce a magma, highly enriched in incompatible elements, while a larger degree of melting will dilute them more, as more of the bulk rock melts.
like squeezing a tea bag, the first bit of water gets the strongest flavor.
A very good analogy, yes.
So what kind of magmas do we get from small degrees of partial melting, say, in the mantle?
Typically, very small degrees of mantle melting produce magmas that are chemically quite distinct. They are often alkaline, meaning rich in sodium and potassium relative to silica, or potassic, specifically high in potassium, or sometimes peralkaline, which relates to the balance of alkalis and aluminum.
Sounds exotic. Any specific rock types?
Yes, some rather unusual ones. Things like lamprifiers, lamprites, and kimberlites, kimberlite being famous as the source rock for diamonds. Also, certain mafic rocks containing the mineral nepheline, like alkali basalts or essexite gabbros, and even carbonatites, those rare non-silicate magmas, can form this way.
Wow. Kimberlites and diamonds from just a tiny bit of melting. What about melting the crust?
Low degrees of partial melting of the crust can produce melts that eventually form pegmatites, those igneous rocks known for their exceptionally large crystals.
Pegmatites, right? Okay, that's low degree melting. What about higher degrees?
Higher degrees of partial melting produce different results. For example, some granite composition magmas are thought to be what we call eutectic or catectic melts. These represent compositions that melt at the lowest possible temperature for a given pressure, and they can actually be formed by a range of partial melting degrees in the crust, from low to high. Fractional crystallization can also produce granitic melts.
So granite can form in multiple ways.
Yes. But if you have very high degrees of crustal melting, you tend to produce magmas that form rocks, like tonalite, granodiorite, or monzonite, though often other processes like magma mixing are involved here too.
Okay. And high degrees of melting in the mantle.
That's where you get things like kumatite, which we mentioned earlier as being very hot and more common in the early Earth, and also piquate basalts, which are rich in magnesium. These require substantial melting of the mantle source.
So the amount of melting is a really critical factor controlling the final magma chemistry. Let's zoom back into the magma itself now. Its structure and properties. You said it's mostly a silicate melt.
That's right. Chemically, silicate melts are dominated by silicon and oxygen, along with significant amounts of aluminium, alkalis like sodium, potassium, calcium, and then magnesium and iron.
And structurally, you mentioned silica tetrahedra.
Yes, similar to solid silicate minerals, the basic building block is the silicon atom surrounded by 4 oxygen atoms, a tetrahedron. But unlike in a crystal where these tetrahedra are arranged in a highly ordered, long-range repeating pattern, in a melt, the arrangement is much more disordered. There's still local ordering, tetrahedra linking together, but it's short-range and constantly shifting. Think of it like a tangled web rather than a neat lattice.
A dynamic, jumbled network. And how does the structure affect how the magma behaves, its physical properties?
The physical properties, things like viscosity, density, how easily gases can diffuse through it, are directly linked to this atomic structure as well as the temperature, pressure, and the specific chemical composition. And viscosity is arguably the most crucial property for understanding magma behavior, especially during eruptions.
Viscosity, its thickness or resistance to flow, like comparing water and treacle.
Exactly. And the key factor controlling viscosity in silicate melts is the silica content.
More silica means.
More silica means more interconnectedness between the silica tetrahedra. They link up to form longer chains and more complex networks. This increased linkage, or polymerization, makes the melt more resistant to flow. It becomes more viscous.
So high silica magmas are stickier.
Much stickier, yes. Felsic magmas like rhyolite, which are high in silica, are very viscous. Mafic magmas like basalt with lower silica are much runnier.
What else affects viscosity? You mentioned water earlier.
Yes, water has a dramatic effect. Dissolving even small amounts of water into a silicate melt breaks some of the links between the silica tetrahedra. It disrupts the network structure.
Making it less tangled.
Precisely. And that drastically reduces the viscosity. A wet rhyolite magma can be significantly less viscous than a dry one at the same temperature.
Interesting. And temperature itself.
Temperature also plays a big role. Higher temperatures mean more thermal energy, the atoms vibrate more vigorously, and can move past each other more easily. So hotter magmas are generally less viscous than cooler ones of the same composition.
Okay, so summarizing. High silica means high viscosity, water reduces viscosity, and high temperature reduces viscosity.
That's the essence of it. So putting it together, mafic magmas like basalt tend to be hot and relatively low in silica, making them low viscosity fluids. Felsic magmas, like rhyolite, are typically cooler and high in silica, making them very high viscosity fluids. Intermediate magmas, like andesite, are somewhere in between.
And this difference in viscosity is critical for eruptions.
Absolutely critical. Low viscosity magmas, like basalt, allow dissolved gases, like water vapor, CO2, to escape relatively easily as the magma rises towards the surface. This usually leads to gentler, effusive eruptions. Think of those fluid lava flows in Hawaii. Okay.
Gases bubble out easily.
But in high-viscosity magmas, like rhyolite, the sticky, tangled structure makes it very difficult for gas bubbles to escape. They get trapped, and pressure builds up and built up. Until the pressure overcomes the strength of the magma and the surrounding rock, leading to explosive fragmentation. That's when you get those massive, dangerous eruptions that produce ash clouds and pyroclastic flows, like Mount St. Helens or Pinatubo.
So viscosity is a major control on how hazardous a volcano might be.
It's one of the primary controls, yes.
Right. This is making a lot more sense now. Can we maybe run through the main magma types again, just summarizing their key features based on what we've discussed, starting with
Ultramafic. Ultramafic magmas, sometimes called picritic, key things. Very low silica content, less than 45%. Very high in iron, and especially magnesium oxide over 8%, sometimes up to 32% NGO.
extremely high magnesium. And temperature.
Extremely high temperature, up to maybe 1500 degrees C.
Yeah.
Because of the low silica and high temperature, they have very low viscosity.
Very fluid eruption style.
Generally gentle, effusive. Found at divergent boundaries, hotspots, sometimes convergent boundaries. But remember, these were much more common in the Archean eon when Earth was hotter. Magmatians are the classic example, but they're rare today.
Okay, ancient, super hot, runny stuff. Next up, mafic or basaltic.
Mafic or basaltic. Silica content is a bit higher, but still relatively low, less than 50%. Iron and magnesium oxide, typically less than 10 weight percent.
Still hot.
Still very hot, up to around 1300 degrees C. Viscosity is low, similar to ultramafic, maybe slightly higher, but still very fluid.
Eruption style also gentle.
Generally gentle, effusive lava flows are typical. This is your classic Hawaiian or Icelandic type eruption. Found widely divergent boundaries, hotspots, convergent boundaries. Basalt is the most common volcanic rock on Earth's surface.
Right, the workhorse magma. Okay, moving up the scale. Intermediate or andesitic.
Intermediate or andesitic. Now, the silica content is noticeably higher, around 60%. Iron and magnesium content drops, maybe around 3%.
Temperature.
Yes, typically cooler, around 1000 degrees C. And with that higher silica content, the viscosity is intermediate. It's definitely thicker than basalt.
And the eruption style reflects that.
It does. Eruptions tend to be more explosive than basaltic ones because gases can't escape as easily. You often get a mix of lava flows and explosive activity. These are very common at convergent plate boundaries, forming volcanic arcs like the Andes, hence the name andesite.
The Andes Mountains, right. Okay, finally, the top end. Felsic or rhyolitic.
Felsic or rhyolitic. Very high silica content, usually over 70%. Iron and magnesium content is low, around 2%.
Temperature. Even cooler.
Yes, typically the coolest of the common magma types, often below 900 degrees C. And because of the very high silica and lower temperature, the viscosity is extremely high, very thick, very sticky.
Oh, and that means
Explosive.
Highly explosive eruptions are characteristic. Think caldera-forming events, large ash columns, expensive pyroclastic flows. Gases get trapped very effectively, leading to violent releases of pressure.
where do we find these?
Often associated with hotspots under continental crust, like Yellowstone National Park, which is basically a giant rhyolitic system, also found in continental rift zones and sometimes in mature island arcs.
Yellowstone. Okay, that really paints a picture of the potential power. Well, that gives us a fantastic and really thorough overview, covering everything from the basic definition right through to the different personalities of magma, if you like.
Yeah, from the deep earth source right up to the eruption style. It's amazing how it all connects.
It really is. It's quite something to consider, this molten rock churning away beneath us, driving so much of the geology we see, the mountains, the islands, the very ground we stand on.
It's absolutely fundamental to how our planet works. And while we've covered a lot today, it's important to remember this is a really complex field. Scientists are constantly learning more, refining the details. Even things that sound simple, like melting rock, have layers and layers of complexity.
Absolutely. But I think this deep dive has definitely given us, and hopefully you listening, a really solid foundation for appreciating the power and the intricacies of magma and how it shapes our world through geology and volcanism.
Definitely. And it leaves you with some interesting thoughts, doesn't it? Like, how might changes in Earth's internal heat budget or subtle shifts in mantle composition over millions, even billions of years have altered the types of volcanism the planet has experienced?
Comparing the komatiites of the Archean to the rhyolites of Yellowstone. That's a big difference driven by deep time changes.
Exactly. It's that fascinating link between the unseen world deep beneath our feet and the often dramatic, sometimes catastrophic events we witness on the surface. Something to ponder.
A brilliant thought to end on. Thank you for joining us on this deep dive into the fiery heart of our planet. Until our next exploration.